Good morning, students. So today's class we are going to study about support vector missions. Support vector missions is a kind of an unsupervised classifier. It's a kind of a machine learning classifier. So in which it can able to classify a binary class or multi classes also. Okay. A very good example for the support vector mission is suppose you want to classify the normal and ECG data. ECG data in the sense abnormal ECG data. So if you want to classify into two class, normal and abnormal ECG, in that case, you can use the support vector machine. It will classify and provide you the output. So that class we call it as binary class. Suppose if you want to do the multi-class. That means in the case of arrhythmias, if you want to classify into multiple class, you know different types of arrhythmias like bradycardia, tachycardia, premature ventricular contractions, trigeminy, bigeminy, etc. So example, if you guys take 5 arrhythmias, in that case 5 classes. So if you want to group the arrhythmias and the normal into multi-class category, we can use this support vector mission. Now, in this support vector missions, you have a terminology called hyperplane. So, what is meant by hyperplane? Hyperplane is nothing but it's like a decision boundary which separates the data, two different data sets. Okay, the two different data here. So, two different classes also we can say. And if you see the line, this line we call it as hyperplane. And the data are spread in the either part of the support vector. So here, these are the data points. That red color points and blue color points are data points. And you can see in some of the data points, it has been circled. So this circled one, we call it as a support vectors. So support vectors are indicated by a circle one. And also in the in this support vector mission, one thing we have to consider that there should be some maximum margin should be there between the hyperplane and the data points. You can able to see that the selected data points have some maximum margin between the hyperplane and the data points. You can able to see the here. Okay. Now let us see how we can able to find out the right hyperplane. Okay, so how we can best segregate the two classes within the data. So here you can able to see this is a hyperplane in which two different data points are located, and you can able to see the margin. There is a maximum distance between the hyperplane and the data points in either sides. Okay, so we have to choose the hyperplane in such a way that there is some greatest possible margin between the data point and the hyperplane. Okay, within the training set. So if you see any data, initially we used to segregate into training set, testing set and validation set. And the data which is used in the training set, which will not be used in the test set. For test set, we will be having the separate data for testing. And the data which is used in the training will not be used for test set. A new set of data are initially we'll segregate in terms of certain percentage and use the data for the test set. Okay. So now the next scenario is identify the right hyperplane. Okay. So the scenario one is identifying the right hyperplane. So here we can see that there are three hyperplanes are there. So those are A, B and C. Now we have to identify which hyperplane is correct one. So now let us consider A. When you see the A, so you can able to see that this is the A hyperplane and check the either side of the A hyperplane. So you can able to see that in one side of the A, we have the stars and then the circles, red circles. Other side you have having the red circles. That means the data are not properly segregated. So the data are unevenly segregated. So in that case, A is not a right hyperplane. Then you consider C. If you consider C, one side if you have star and circle, another side you have the circle, red color circles. In this case also, two set of data points are located in one side of the hyperplane. Another data point is located in another set of hyperplane. C is not the correct hyperplane to segregate. Also, you can see the data points are lying on the hyperplane. That is also not a correct one. Okay. So now you see the B hyperplane. So if you see the B hyperplane here, the B, you see, check the either side of the B hyperplane. So one side you have only the star, other side you have the red circles. And also you can able to see the maximum margin between placed between the data point and the B plane. You can either side of the B plane you can check with these two different data. Maximum margin is present. So we can say that B hyperplane is an excellently performed this job. So B hyperplane is the best one. Next scenario. In scenario 2, here we have three hyperplanes A, B and C. Now we have to identify which is the right hyperplane. So here if you see B, you take the B hyperplane, you can able to see the data points are very much closer to the hyperplane. And if you take the A hyperplane, the data points are very much closer to the hyperplane. There is no maximum margin is present. And when you take the C hyperplane, from C to the data points on either side, definitely there is some maximum margin is there. Then we can say that C is a best hyperplane which segregates the data. Okay. So here, how we can able to select the right hyperplane based on the maximum distance between the nearest data point and the class, either class. So that will be the right hyperplane. So here C is considered as a right hyperplane. Next. So this is the third scenario. In this case, how we can able to classify the data. So you can able to see that one set of data star, it is clustered and arranged in one place. Another set of data, which is the red color circles, which is located in the other place. So in that, this data star is located here in the red color one, which is the odd man out. So this one, we call it as outlier. That means we can eliminate it because it is very difficult to classify this in this case. So in that case, we can consider this as an outlier and we can ignore it. Then in the fourth scenario, there are two hyperplanes are there and data points are scattered here. So we have to select which one is a better hyperplane. And if you take B, so if you take B, it is a higher margin is there. When you compare to A, higher margin is there. But when you see the B, in this one side you have the star, another side you have star plus circles. So it does not equally classify the data. So we cannot consider as B. Now you take A. So in A, even you have not maximum margin, but it is exactly segregates the data into two different class. One set of data lies, circles lies in one side, another circle, stars is lies on the other side. So it equally distributes the data. So in that case, a hyperplane A is considered as a best one and B as classification error. Now, let us go to solve one linear examples with respect to the support vector mission. So, the given question is, you have given a positively labeled data points and negatively labeled data points. So, now we have to map these data points in the graph and then we have to choose the support vectors and then check how we can able to separate into two different class. So, that is our ultimate aim. So now you can see the positively labeled data points as 3, 1, 3, 1, 3, minus 1, 6, 1, 6, minus 1. And the negatively labeled data points 1, 0, 0, 1, 0, minus 1, minus 1, 0. This is the data points. Now, these data points, we have plotted it. Okay, so we have plotted it. So the positively labeled data points are plotted with the blue and negative points are plotted with red. So we have plotted the two different data here. This is a support vector plane. Now the next step, here we have to choose the three support vectors. So now in this The chosen three support vectors are these data points. So one is this one, which is 1, 0, then 3, 1 and 3, minus 1. So these three are the data points which is chosen as a support vector as S1, S2 and S3. The next step, you can able to see that the chosen support vectors are marked as yellow color one. So we have marked the support vectors are yellow color one, positively data points as +1, negatively data points as -1. So we have to select a suitable hyperplane which segregates the data. That is our ultimate game. So how we are going to do that, we are going to see now. So now with the support vectors, we need to augment a bias input as 1. So if you see S1, we have 1 and 0. Now the S1 bar, the approximate version, we call it as 1, 0 and 1. That means the bias input is added at the end. Similarly, for S2 it is 3, 1 and the bias input 1 is added, and that we call it as 3, 1, 1. We call it as S2 bar. And S3 is 3 minus 1. The bias input is added here. So that is call it as 3 minus 1, 1. We call it as S3 bar. Now we have defined that estimated support vectors. S1 bar, S2 bar, S3 bar. So with that, we have formulated a mathematical equation. So according to that equation, we have an unknown parameter alpha 1, alpha 2 and alpha 3. And here with the equation, it is S1 into S1, S2 into S1 and S3 into S1. That means the support vector X1, S2, S3, it is multiplied by S1 and it is equated with -1. And in the second equation, you can observe that alpha 1, alpha 2, alpha 3 is common, and S1, S2, S3, it is multiplied throughout the equation with S2 and it is equated to with +1. And in the third equation, when you see alpha 1, S1 bar, S2 bar and S3 bar, it is multiplied with S3 bar. Okay, and it is equated with +1. Now, according to this, our aim is to identify the unknown value alpha 1, alpha 2 and alpha 3. Now, we know that S1, S2, S3, when you substitute those values here and then multiply these two matrix equation, so you'll be getting a refined equation. So, this is a set of equation you will be getting. So, according to that, it is 2 alpha 1 plus 4 alpha 2 plus 4 alpha 3 equal to -1. 4 alpha 1 plus 11 alpha 2 plus 9 alpha 3 equal to +1. 4 alpha 1 plus 9 alpha 2 plus 11 alpha 3 equal to +1. Now, we have to solve this equation in order to find out alpha 1, alpha 2, alpha 3. So, after solving this equation, we are getting -3.5, 0.75 and 0.75. Then we are substituting in this equations estimated weight equal to summation I, AI, SI bar. In that, alpha 1, alpha 2, alpha 3 value we know, we have substituted, and the SI bar is nothing but the support vector S1, S2 and S3 we have substituted. When you multiply it and simplify, you will be getting 1, 0, -2. So from these vectors, we can identify that 1 and 0 represents the weights and -2 represents the bias. Okay, so we can form the hyperplane equation as y equal to wx plus b, where w is 1 and 0 and bias b is -2. Now we have chosen the correct hyperplane vectors as 1 and 0. So accordingly, according to 1 and 0, we have marked after 1 and 0, we have marked the hyperplane. This hyperplane only, it separates the classes into two different classes, positively data points and negatively set up data points. So this is a hyperplane which separates the two different classes. Okay, so this is how we can able to separate it. So now, what is the applications? What is the application of this particular support vector mission? So where it can be used? So that is very important. This is we have studied the concept of what is support vector mission, what is a hyperplane, and how we can able to solve the support vector mission using the linear problem. So these things we have studied. Now we have to see what is the application point of view, where and all it is applied. So it is not only applied in signal processing, it can be applied in image processing also. Okay. So if you see the signal processing, any kind of classifying the data into normal and abnormal, either it may be an ECG signal, or it may be an EMG signal, or it can be EEG signal, any kind of biosignals, we can classify either into two class as binary class or into a multi-class. Okay. So example, in if you see the EEG data, if you're taking the EEG data for a subject with the different state, when a person is in normal state, when a person is in sleep state, deep sleep state, or when a person in semi-sleep state, or when a person is active and when a person is normal. So in all these brain states, we are acquiring the EEG. And then after acquiring the EEG, what you can do? You can extract the features from this. It features can be any statistical features. You can extract the features from this. After extracting the features, these feature values will be given as an input to the classifier, that is like SVM classifier. It will segregate and provide you the output as in terms of multi-class. That means you have in, as I said, the example, the SVM will provide the output as a normal person in normal state, deep sleep state, semi-sleep state, or the person is in drowsiness, or person is in active or hyperactive state, like that, it can classify and gives you the multi-class output. So that is an application of SVM. So it is a kind of a unsupervised classifier. So that is one of the applications of the support vector machines. So along with support vector machines, you have different classifiers also there, like random forest, K and K nearest neighbor. So like that, we have different types of classifier available. But among that, this support vector machine is a very good classifiers which can be used for classifying the normal and abnormal signal in terms of binary class as well as multi-class. Okay. Um, so that is possible using the support vector machine. So thank you for watching.